This paper presents a comprehensive theoretical analysis of quartz plate acoustic wave resonators and sensors, utilizing three-dimensional equations of anisotropic elasticity or piezoelectricity. It encompasses both classical results on acoustic wave resonators and new applications in acoustic wave sensors, delving into basic thickness modes with various complications and more intricate transversely varying modes. The analysis incorporates effects due to electrodes, mass loading, contact with fluids, and air gaps, as well as the behavior of shear horizontal and straight-crested modes. This in-depth review is foundational for understanding and designing quartz crystal plate resonators and sensors. In the realm of quartz crystal technology, various orientations of quartz plates are crucial for their applications. These orientations, referred to as plates of different cuts, are specified by two angles phi and theta with respect to the crystallographic axes, x, y, z. A particular cut is called a doubly rotated cut, with the stress-compensated SC cut being an example with phi, theta, equals 22.4 degrees, 33.88 degrees. Plates of different cuts have different material matrices with respect to the coordinate system, x1, x2, x3, in and normal to the plane of the plates. The rotated Y-cuts, including the widely used AT cut, exhibit monoclinic symmetry of class 2 or C2 in the plate coordinate system, x1, x2, x3. This symmetry is fundamental for understanding the anisotropic properties of quartz, which are critical for its applications. The material matrices and governing equations for the displacement vector U and the electric potential phi are detailed, including the stress and electric field components. These equations highlight the anisotropic properties of quartz, demonstrating how they contribute to its unique characteristics. The study of these properties is essential for optimizing the use of quartz in various technologies, such as oscillators and sensors. The analysis of quartz plates, particularly for finite plates with boundary conditions, is complex, even with approximations, due to the difficulty in obtaining analytical solutions. It is crucial to consider piezoelectric coupling for frequency analysis, especially in resonator and sensor applications. The paper focuses on thickness modes in rectangular quartz plates, reducing the system to uncoupled groups of equations for thickness modes. The solvability of problems related to thickness modes is mathematically tractable, and the thickness shear mode in the x1 direction is significant, as it can be conveniently excited by a thickness electric field. The discussion also highlights the difference between elastic and piezoelectric analyses, including the effects of piezoelectric coupling on resonance frequencies. In acoustic wave sensors, the distribution of thickness shear, TSH, deformation and modes along the plate thickness is significantly influenced by the air gaps between electrodes and the crystal plate. The fundamental mode plays a crucial role in device performance. However, environmental effects such as temperature changes, stress, and additional surface structures like mass layers, fluid contact, particles, and fibers can alter the resonance frequencies of TSH modes. This sensitivity to environmental factors is critical for resonator-based acoustic wave sensors, which have broad applications. The presence of mass layers, in particular, has a profound impact on TSH modes. Quartz crystal microbalances, QCMs, are commonly used for mass sensing, relying on the Sauer-Bray equation to describe mass sensitivity. This equation relates the changes in resonance frequency to the mass deposited on the crystal surface. In addition to the Sauer-Bray equation, other analytical approaches have been developed to understand the effects of mass on crystal plates. These approaches provide valuable insights into the complex interactions between the crystal plate, electrodes, and environmental factors, ultimately enabling the optimization of acoustic wave sensors for specific applications. By understanding and controlling these interactions, researchers can develop highly sensitive and selective sensors with improved performance and reliability. The resonant frequencies of a crystal plate are influenced by various factors, including the bonding between the mass layer and the plate. Imperfections in this bonding can either decrease or increase the resonant frequencies, depending on the specific conditions. When the mass layer is not extremely thin, its shear modulus also plays a significant role. Furthermore, fluids in contact with the plate can reduce the resonant frequencies, making this phenomenon useful for fluid sensors. The presence of particles or fibers on the plate can either increase or decrease the frequencies, depending on their properties and interactions with the plate. To analyze these effects, various models are employed, including the shear-slip model. Mathematical approaches such as elasticity and piezoelectricity theories are also utilized to provide a comprehensive understanding of the phenomena. A detailed examination of the effects of fluids, particles, and fibers on the resonant frequencies reveals the importance of considering these factors in specific applications. For instance, the viscoelastic properties of fluids and the mechanical properties of particles and fibers significantly impact the resonant frequencies. The shear modulus of the mass layer and the bonding conditions between the mass layer and the plate also play critical roles. By understanding these complex interactions, researchers can optimize the design of crystal plate-based sensors and devices for various applications. The dynamic analysis of a TSH resonator, focusing on transient effects during startup or turning off, was conducted to complement time harmonic analyses for frequency behavior. This study highlights the importance of understanding edge effects in real devices due to their finite size. The operating TSH modes exhibit slow in-plane variations in the x1 and/or x3 directions, referred to as transversely varying TSH modes. Specifically, modes with in-plane variations along x3 only are called shear horizontal, shish, or anti-plane motion, described by equations 5, and governed by equation 6. This simplification represents an important class of problems for which theoretical results can be obtained. The discussion includes shish motions, including face shear, FS, and thickness twist, TT, modes, with elastic and piezoelectric solutions for these waves. Dispersion curves for FS and TT waves are presented, highlighting the effects of mass layers and interface elasticity on these curves. The interaction between in-plane and shear elasticity with mass layer inertia significantly affects wave frequencies in quartz plates on elastic half-spaces, generalizing love waves in elasticity. This is particularly relevant for understanding the behavior of flexural shear, FS, and thickness twist, TT, waves, as well as waves in plates with non-uniform material properties. The case of a quartz crystal microbalance, QCM, carrying a porous mass layer has also been extensively analyzed. For shish vibrations of a finite plate, FS and TT modes are coupled by boundary or edge conditions, leading to frequency spectra. Figure 6 displays the frequency spectra of an AT-cut quartz plate, where data points representing mode frequencies under various aspect ratios C, B form curves that can be classified into two families: FS-dominated modes with steep curves and TT-dominated modes with gradual curves. The intersection of these curves indicates strong coupling between TT and FS modes, which is undesirable in device operation. The frequency spectra are useful for excluding discrete values of C, B associated with strong mode couplings. The inertia of partial electrodes or mass layers causes in-plane mode variations in a plate, leading to energy trapping and Beckmann's number. This is illustrated in Figure 7, which shows an unbounded crystal plate with partial electrodes, demonstrating the concept of trapped energy resonator. Trapped modes in partially electroded piezoelectric plates are crucial for designing resonators and quartz crystal microbalances. Dispersion curves of a TT wave in an infinite plate, either unelectroded or fully electroded, explain the existence of trapped modes. The inertia of the electrodes lowers the frequency, resulting in a range between the cutoff frequencies where the wave number in the electroded region is real, while it is purely imaginary in the unelectroded region. This leads to oscillatory behavior under the electrodes and exponential decay away from the electrode edges in the unelectroded region. Multiple trapped modes can exist between the two cutoff frequencies, each with a different number of nodal points along the x3 direction. However, only the first mode without a nodal point in the x3 direction is typically desired in applications. Reducing the electrode length eliminates undesirable modes one by one until only the desired mode remains, as observed by Beckmann. Beckmann's number is defined as the ratio of the electrode length over the plate thickness below which only one trapped mode without a nodal point in the x3 direction exists. Previous studies have investigated trapped TT modes, including the determination of Beckmann's number. Additionally, the use of elastic shush modes for AT-cut quartz plates has been explored. By neglecting C56 due to its small value compared to C55 and C66, elasticity problems can be solved over rectangular domains using trigonometric series. This approximation is useful for understanding partially electroded rectangular resonators, such as the one shown in Figure 9, where a trapped mode exhibits vibration mainly under the electrodes and decays away from their edges. Figure 9a illustrates a finite plate with partial electrodes, where the electrode size is 2C equals 40 mm. The effects of electrode size on energy trapping of the first thickness twist (TT) mode are showcased in Figure 9b, revealing that the energy trapping efficiency increases as the electrode size increases. In resonator manufacturing, electrode mismatches between the top and bottom electrodes often occur, as depicted in Figure 10a. This mismatch poses a challenging problem in modeling, with limited theoretical results available, such as those presented in 61. While frequencies and modes may not be significantly affected, electrical admittance may be sensitive to electrode mismatch, necessitating a piezoelectric analysis. Previous studies have explored various configurations, including a quartz crystal microbalance (QCM) with a single mass layer, 62, a plate with two pairs of electrodes as a filter, 63, a plate with multiple mass layers as a QCM array, 64, and a mesa resonator with stepped thickness, 65. These studies demonstrate that TT vibration can be trapped under certain electrodes or mass layers, with longer or thicker mass layers exhibiting better energy trapping. Moreover, research has addressed non-uniform mass layers and imperfect bonding on QCMs, 15, 66, 69. These studies reveal that not only frequency but also energy trapping is sensitive to mass layer thickness variation and interface bonding. The research focuses on X1-dependent modes, particularly the governing equations for straight-crested modes with in-plane variations along the X1 direction. It presents a simplified case of elasticity, demonstrating highly coupled equations. The paper then explores propagating waves in an infinite plate, which can be formally obtained in general. For AT-cut plates, these waves are studied in detail, separating into symmetric and antisymmetric waves based on whether U1 is an even or odd function of X2. The dispersion curves of antisymmetric waves are shown in Figure 11, revealing multiple curves representing different branches of the dispersion relations. In the long wavelength limit, the wave number and frequency approach zero, causing the governing equations to degenerate into Cauchy's equations, corresponding to specific dispersion relations. Understanding these modes and their behavior is crucial for the design and operation of resonators and mass sensors, as depicted in Figure 10. The discussion on vibrations in piezoelectric plates focuses on extensional, flexural, and FS motions, highlighting the dispersion curves for these modes. It emphasizes the antisymmetry of flexural and FS motions. The section also covers the propagation of straight-crested waves along the X1 direction in a quartz plate with symmetric electrodes, as well as the analysis of waves in doubly rotated cut quartz plates exhibiting monoclinic symmetry. Additionally, it mentions the piezoelectric solution of straight-crested waves propagating in a plate of triclinic crystals and the study of coupled TSH and flexural vibrations in AT-cut quartz plates. The problem of modes depending on both X1 and X3 directions, requiring 3D approximations for solutions, is also addressed. The 3D piezoelectric equations for quartz plates and their various approximations are comprehensively reviewed, along with solutions to different models. These equations provide a fundamental understanding of the behaviors of resonators and acoustic wave sensors, serving as benchmarks for various approximation techniques. The results from piezoelectric analyses are applicable to langasite, a crystal belonging to the same class as quartz but with higher piezoelectric coupling. Moreover, some theoretical studies on quartz plates may be applicable to the analysis of plates of lithium niobate and lithium tantalate or other crystals. The energy trapping effect of the fundamental TSH mode in a partially electroded resonator is illustrated in Figure 11, courtesy of Professor Ji Wang of Ningbo University. This concept is crucial in understanding the behavior of resonators. The paper highlights several key findings, including the significance of accurately modeling the piezoelectric behavior of quartz plates and the importance of considering the effects of electroding and energy trapping on resonator performance. The comprehensive review of 3D piezoelectric equations and their approximations provides a solid foundation for the analysis and design of resonators and acoustic wave sensors. The applicability of these results to other crystals, such as langasite, lithium niobate, and lithium tantalate, emphasizes the versatility of the presented approach. The paper's conclusions underscore the need for continued research into the complexities of piezoelectric behavior and its applications in sensor technology. Thickness shear vibration of piezoelectric plates, particularly rotated Y-cut quartz plates with electrodes of unequal thickness, is a crucial area of research. Previous studies on piezoelectrically forced vibrations, such as those by Tiersten, Yang et al., and Wang et al., have laid the foundation for this investigation. The present work aims to derive a more accurate and comprehensive mathematical model, incorporating the effects of electrode thickness on the vibration characteristics of these plates. The researchers employed a variational approach, utilizing the Hamiltonian principle, to formulate the governing equations for the thickness shear vibration of the piezoelectric plates. The resulting equations were then solved using a perturbation method, which allowed for the extraction of the vibration frequencies and mode shapes. The study reveals that the electrode thickness has a significant impact on the vibration characteristics, particularly at higher frequencies. The unequal electrode thickness introduces anisotropy in the plate's stiffness, leading to a deviation from the ideal thickness shear vibration mode. The researchers also conducted a series of numerical simulations to validate the theoretical model, demonstrating excellent agreement between the calculated and simulated results. The findings of this study have important implications for the design and optimization of piezoelectric devices, such as sensors, actuators, and energy harvesters, where precise control over vibration characteristics is crucial. Future work involves extending the current model to account for additional factors, including the effects of damping and external loading, to further enhance the accuracy and applicability of the results. Quartz crystal microbalances, widely employed in sensing applications, exhibit complex frequency responses influenced by mass and liquid loading. A thorough examination of existing research reveals that the quartz crystal's resonance frequency decreases with increasing mass loading, a phenomenon attributed to the added mass and stiffness of the deposited material. Conversely, liquid loading induces a dual frequency response, with the higher frequency corresponding to the quartz crystal's resonance and the lower frequency resulting from the liquid's viscoelastic properties. Studies have demonstrated that the Sauer-Bray equation, which correlates the frequency shift to the deposited mass, remains a reliable model for describing the mass loading effect. However, its limitations become apparent when considering liquid loading, where the equation's assumptions of a rigid, uniform layer are no longer valid. Alternative models, such as the Kanazawa-Gordon equation, have been proposed to account for the viscoelastic properties of liquids, but their applicability is restricted to specific experimental conditions. The influence of liquid properties, including viscosity, density, and surface tension, on the quartz crystal's frequency response has been extensively investigated. Research has shown that increasing viscosity and density led to a decrease in the resonance frequency, while surface tension affects the frequency response in a more complex manner. In addition to these fundamental studies, researchers have explored the application of quartz crystal microbalances in various fields, including biosensing, electrochemistry, and materials science. The development of novel sensing technologies, such as quartz crystal microbalance-based immunosensors, has been facilitated by a deeper understanding of the underlying physical principles. Despite the significant progress made in characterizing quartz crystal microbalances, several challenges and limitations persist. Future research directions include the development of more accurate models capable of describing the complex interactions between the quartz crystal and liquid environments, as well as the exploration of new sensing applications that exploit the unique properties of these devices. The provided page from the research paper presents a comprehensive list of methodologies employed in the study, including data collection, statistical analysis, and model validation. The authors emphasize the significance of their approach, highlighting the novel use of machine learning algorithms in predicting climate patterns. The section details the equations and algorithms used, stressing their importance in capturing the complex relationships between environmental factors. Research on quartz crystal plates has delved into the complexities of stiffness, bonding, and mass effects on their vibrations. Studies have examined antiplane vibrations, high-frequency vibrations, and dispersion relations, shedding light on the impact of mass layer stiffness and imperfect bonding on quartz crystal microbalances. Vibration modes of quartz plates with monoclinic symmetry have been investigated, revealing the significance of dispersion curves for infinite piezoelectric plates. The Eckstein functions have been utilized to model high-frequency vibrations, while Beckmann's number has been calculated for harmonic overtones. Furthermore, the radial dependence of mass sensitivity in modified electrode quartz crystal resonators has been analyzed, providing insights into the thickness shear vibration of rectangular quartz plates with partial electrodes. These findings have far-reaching implications for the design and optimization of quartz crystal-based devices. The research has demonstrated the importance of considering the interplay between stiffness, bonding, and mass effects in understanding the vibrational behavior of quartz crystal plates. By exploring the complexities of these interactions, researchers can develop more accurate models and improve the performance of quartz crystal-based devices.